This video is kind of a summarization and also has some visualization ideas for dual spaces and maps. It does help to have seen the complete video with lots of different examples, but here I'll review some of the definitions and then get into visualizations. We'll start with the definition of a linear functional on V. So a linear functional is a map that maps from the vector space V to the scalars. And so it is an element of the set of linear maps from V to F. Once we have this set of functions from V to F, we can define addition of these functions as well as scalar multiplication on this function such that we have a vector space, and that's called the dual space denoted V prime. So that's the vector space of all linear functionals on V. Again, V prime is the set of linear functions from V to F. And now that we have this new vector space V prime, we want to create a basis for it. And what we do is we start by looking at a basis for V, so our original vector space. So if V1 through Vn is a basis, then we're going to use this basis to make a dual basis for V prime. One thing I feel like is worth mentioning, and I really like this about your book, is that your V and your W, your regular alphabet, is used to denote vectors on your original vector space V. Then these Greek letters, phi, theta, gamma, are used to represent vectors in your dual space, V prime. So these vectors are definitely functions from V to F. That is not to say that your vectors in V are not functions. They might be, they might not. But this emphasizes the difference between your vector space when you're talking about vector space, your original vector space V, and then your dual bases where they are definitely functions. So we're thinking of these as functions that map V to F. We're thinking of these as regular vectors on V. So we're going to define each of our basis vectors, phi sub j, and again, each of these phis, they map from V to F. So they take a vector V sub k, and they map it to the scalar. And we're going to map it to the scalar 1 if j equals k, 0 if they are not equal. So the look of this basis is totally analogous to the standard basis of, say, Rn or your standard basis of polynomials. And it's analogous in that the ith basis vector, so for example, the first vector basis, has a 1 in the ith spot, right? The second vector in your basis has a 1 in the second spot, and it has 0 everywhere else. This is what is going to allow you build other vectors and also decompose your vectors. So again, something worth remembering is that this basis vector picks out the jth component of your vkth vector. So in this way of creating your dual basis from your basis V, we've used the fact, without proving in this video, that the dimension of your dual basis is going to equal the dimension of your original vector space V, right? So they're both n. And this is proven in your book and also in my previous video, and it uses this fact here, which you should know. So the dimension of the space of linear maps from V to W equals dimension of V times dimension of W. The last thing I want to talk about when I talk about duals is the dual map. So let's review the definition. So if T is a linear map from V to W, then the dual map of T, denoted T prime, is in the space of linear maps from W prime to V prime defined by T prime of phi is equal to phi composed with T for phi in W prime. To help me understand this, I'm going to draw some pictures. So I have a vector space V, and I have the vector space W, and I have this linear map T that takes vectors from V to vectors in W. So far what I've drawn is this part here, that T is a linear map from V to W. So the next part of this definition I'm going to look at is that we have these phi that are in the dual of W. And again, the dual of W is in the space of functions from W to F. So that's going to look like, here I have F, and I have things that take elements of W maps it to F. And these are functions that are in my dual of W. Again, the dual of W takes things from my vector space and it maps it to the scalars. So the next part of the definition I'm going to focus on is here, and that I'm going to say that T prime is a linear map from W prime to V prime. And the first thing I'm going to say, what's going on here? All of a sudden we have this dual space V prime. Like I didn't draw anything from V to F here. However, there is a mapping from V to F. It's just that it goes through W. So next I'm going to focus on this part of the definition here, which I rewrote over here, which is the dual map of phi is equal to phi composed of t. So again, that's just from the definition. So we're going to look at this function composition and see what it does to a vector v from our original vector space. So first we have a vector v. We apply t to it here, and we get a vector in w. So now that we have our vector in w, we apply phi, and we get a scalar. So here we have an element of f. So again, we've gone from the vector space v to the scalars. One last point. My dual map does not take vectors from v to f. What it does is it takes functions from the dual of w and then gives me a function here, this function composition, that'll then get me to from v to f. So the dual map is a way that takes maps from w prime and gives you another map that goes from v to f. So that's what this means here. So this is my summary and kind of visualization for duals. And next I have this bonus kind of summary slide of products and quotients. I start by reviewing what a sum of sets is, and if you have subspaces u1, u2 up to um, then the sum of sets, denoted this way, is basically u1 plus u2 up to um, where the u1 comes from set u1, the vector u2 comes from set u2, etc., to the vector comes from set So you can think of these are all the different linear combinations where your scalar coefficient is equal to 1 of vectors from set 1, set 2, up to set m. And then this sum of set is a direct sum if each element here of u1, the vectors u1 plus u2 up to can be written in only one way. So it's kind of this idea of independence. It's not exactly linear independence because you can't do coefficients and stuff, but it's sort of the idea that each element sort of is, they're sort of not made from each other. And to show that if you ever are asked to show something is not a direct sum, I'm just going to say the easiest way of doing that is to try writing 0 in two ways. And the reason is the first way you write 0 is it's 0 plus up to from each of your u sub I, you take the zeros, and that's equal to 0. And then what you want to do is try to find, look at the space, u1, u2, so that maybe somehow you can have u1 plus u2 also equal to 0. So again, that's the easiest way, that's the strategy I would do if I wanted to show something was not a direct sum. Next, we have the definition of a product, a cross product of vector spaces, and that's just v1, v2, it's like the m tuple, where each v sub I comes from the vector space v sub I. And there's this a kind of natural mapping from the sum of sets, or a direct sum, into, from the product space into the sums, and that's if you have these vectors u1 through listed as an m tuple, you can then just add each one, and then you're in the direct sum space. For now, I'm going to skip this theorem and go on to the quotient space. So if you have a vector space v divided by u, that's the set of all vectors v. For each vector in the space v, you're going to add it to u, and so you shift u by the vector v. And so the quotient space is sort of the set of subspaces, parallel, and I put this in quotes, parallel to u because they're shifted from u. I saved these two theorems to talk about together because they kind of have a nice sort of relation, and that if you have a direct sum, the dimension of your direct sum is just equal to the sum of your individual vector spaces. And again, direct sum is related to product spaces. So when you have the product or the direct sum, you add the dimensions together. Whereas if you have the quotient space, the dimension of the quotient space is the dimension of the larger space minus the dimension of the subspace space. So again, for product space direct sums you add, for quotient you subtract, and so I kind of like the addition subtraction relation. And that's it for my quick bonus slide on quotients and products. Thank you for listening. Bye-bye.